and welcome to ME330 Computational Tools for the Spring 2022 semester. Really glad to have you all here. I think you're going to be really excited to take this course as we get through it. There's going to be a lot of information that's going to be really useful for you in your careers and as you move into capstone. My name is Dr. Paris von Lockett. I have a PhD in mechanical engineering. I'll talk a little bit more about myself later, but for right now, let's go and get into the class. So as I said, this is mechanical engineering, computational tools, and really what we've tried to envision with this particular class is a holistic training program and how to teach students how to use these computational tools and how to be familiar with them from earlier in their career than maybe they'll actually have the theory. So yes, you want to learn the theory, but we want to get you involved in the application. Where did this come from? Well, the mechanical engineering department has a list of advisors, industrial partners, and those industrial partners said to us, look, we want to make sure that the students who come to us have not only sort of familiarity with these things, but that they've been using them for a while. So they didn't just pick it up in capstone, that they had it in an earlier course, they learned how to do the ins and outs of these simulation methods and these programs then, and then they use the software in capstone, and then by the time they get to us, they've actually done a few things with it. So this is the beginning course in that particular sequence, originally developed by Reuben Kraft and some other folks who are the expertise in solid mechanics and ME. And it started with this third year class, ME330, and then after this we move into the fourth year classes where you can take an introduction to finite element class, which will tell you more about the theory of FEA and also some applications of FEA, that's ME461. Additionally, you can take ME423, computational fluid dynamics, so that'll verse you in the numerics and the applications of the numerics to solve fluid mechanics problems, and those are kind of the two sides of the house. The FEA deals more with solid mechanics and some thermal and heat transfer, whereas the computational fluid dynamics, as the name suggests, deals with the fluid flow problems. So after the fourth year, if you're so inclined, you can stay on for grad school, or maybe you're advanced, you have some extra credits, you can take some grad classes if they'll let you do that. You can take ME563, nonlinear finite elements, and there you'll deal with higher end modeling techniques for plastics or for large deformations, things that don't behave linearly, as we'll get into when we talk more about the theory. Or ME523, so numerical solutions applied to heat transfer and fluid mechanics problems. So again, graduate level stuff, but pertaining to that sort of thermal fluid side of the house. To put it sort of easily and bluntly, our objective here is to provide the best training in the world for numerical computer simulations. We want you guys to have, after this particular sequence of modules that we're going to provide for you, some top-notch training that will allow you to go out and make an impact from day one when you're on the job, and even from here, day one when you're in capstone. Can you apply these methods to solve some tough, non-trivial engineering problems? So, a little bit about myself. My name is Dr. Paris von Lockett. I earned my PhD in mechanical engineering from the University of Michigan in 1999. Before that, I was at Trinity University, oddly a very small, comprehensive liberal arts university in San Antonio, Texas, but I got a very deep appreciation for numerical methods in the undergraduate research that I did there. My background is mostly in plastics and polymers and smart materials, really magnetically active smart materials, but I do a good deal of computational optimization, computational simulation using finite element methods, and also moving into using some fluid dynamics computational methods as well, coupling magnetics, coupling solid mechanics, coupling fluids in the design of different types of structures for biomedical applications and some other things. Before I worked here, I worked at Rowan University, where it's a small comprehensive teaching school in their engineering department when they first started that engineering department. So there we were really focused on undergraduate education, and I sort of brought that as one of my foci here, really committed to making sure that undergrads get the best out of their education possible such that they can go on and do great things. In the past few years, I've been elected a fellow of the American Society of Mechanical Engineers, and I've also won one of Penn State's Engineering Alumni Association's Outstanding Teaching Awards. So yeah, this is kind of my thing. And also when I was at Rowan, I helped design a course like this, so I really like this stuff. If you're interested in learning more about me and more about what I've done, you can read sort of this third paragraph. I've got some funding from the National Science Foundation now to look at advanced additive manufacturing techniques and really this idea of a universal 3D printer and how we can go about doing that using electromagnetic processing. I'm head of the Magneto-Active Composites and Structures Lab at Penn State, and you can check out my website there to see more about that. Or if you're interested, just shoot me some email, and I love to talk about that stuff as well. So today, traditionally syllabus day, first day of the class, we'll talk about the syllabus. As it says, the title is Introduction to Modern Computational Tools for Mechanical Engineering, or we call it Comp Tools. No real prerequisites for this one, no textbook required. Time and place. This is an interesting class in that it was always meant to be web-based because we have students from University Park, we have students from the satellite campuses as well. So you can access all the materials asynchronously online that I'll be presenting here as your instructor. In addition to that, we have recitation sections, which I'll get to in a minute, that are headed by our teaching assistants. Those you can go to get some directed homework help and help with assignments or ask questions. We'll also have discussion boards available. These you can access any time of the day. You can post questions, and either myself or one of the other instructors or one of the other teaching assistants will respond to those. And hopefully the discussion boards will be a repository for people who have questions. If a lot of people have the same questions, we can just post them there, and so you can get those answers. Those discussion boards will roll on and off from one week to the next based on our topics, and so as one topic comes up, we'll have questions about it answered, and then once that module is done, we'll move on to the next topic. We'll have another discussion board. Right now, the instructors are myself, Paris Von Lockett, and Samuel Grauer. He'll come on in about week 8 or 9 to talk about the computational fluid dynamics portions, give you assignments and lectures and topical content in that area. Office hours, generally by email. Shoot me some email. We can come up with a time to either Zoom or meet in person. And the teaching assistants for this semester are Zachary Hertel, Ian Norris, and Kei Zhu. All three of these folks are really interested and well-versed in computational methods, and so they'll help you get through the assignments, the sort of nuts and bolts of how things are done. So on the right, you can see an overview of the planned topics. This week it's going to be Introduction to SolidWorks. Like I said, today's syllabus day. How do we access SolidWorks online? Those are going to be the big things that we'll work on. We'll also then move into weeks 2 through 8, talking about structural and thermal topics. Again, that's the finite element or FEA section. Beam bending, stress concentrations, large deflection analysis, modal analysis, dynamic response, buckling, and heat conduction and convection. And then weeks 9 through 15, when Dr. Grauer comes on, he'll begin talking to you about more thermal problems as he segues into computational fluid dynamics. So viscid and laminar flows, and then flows over a cylinder and airfoil, some application stuff there, and then boundary layer solutions, heat convections, and end up with this idea of what's turbulence like in a pipe, which is a fairly complex problem that I'll have you go into. Now, one particular hallmark of this class as we go through these different topics within FEA or within CFD is that we're going to try and link together both analytical theory, so by hand calculations and solutions. Some of these things you've done already, some of these things you'll be doing a little bit later on in your career, but link those by hand calculations and solutions with how you would go about solving similar problems or equivalent problems, better way to say it, in a computational setting like a finite element analysis, sort of working through SolidWorks. So what's cool there is, we can work out what the solution will be, and then we bring up this numerical method to move toward trying to generate solutions for a similar problem. So we can kind of verify our solution method. That's really going to be the basis for how we approach things, and that also makes it a springboard for, look, if we know how to go about solving these problems, we're confident with our methods because we've had this verification, then we can go about using similar methods to solve even more complex problems. And that's really the springboard approach here. We give you the basics, you get confidence and well-versed in the basics, and then you go off and you design the new things that are going to change the world. All right, so the structure of this course overall. Big picture, what happened is that the solid mechanics faculty in the department here came together and we decided, what are the big fundamental concepts that we can group things into that students need to come away with an understanding of. You know, when they leave this class, what should they know how to do in FEA? And what we decided is that, okay, we're going to start with these sort of linear problems that are small deformation, where everything tends to follow Hooke's law. And so over here on the far left, what you see is kind of in this sort of light blue. We'll have an introduction to SolidWorks. We'll talk about how you can do stress and strain analysis within SolidWorks. We'll look at beam problems. Beams are a good entry point because you should have a strong understanding of beams, plus we can do those solution methods analytically. After that, we'll sort of look at stress concentrations and multi-axial stress. So if you've got more than one loading on a thing, or that thing has some sort of curvature to it, some sort of hole in it, some sort of corner that gives it a stress concentration, how do we apply methods to solve those to get the answers that we pretty much already know from our analytical solution methods? We'll end with an interesting segue into real world problems, which are contact stresses. So here, week 3, you see we've got a device. It's actually a pair of pliers. The pliers are meant to actually grasp onto something while being loaded by your hands. And then it's that interaction of the material within the plier with the thing that you're grasping onto as it's being loaded by the user that makes it sort of closer to a real world analysis and a real world problem. Weeks 4, 5, and 6, you see we move from frequency analysis or modal analysis. So we're looking at what happens to something when it's subjected to cyclic loads or cyclic response. After that, we look at materials that are, or I should say models that deal with nonlinear materials, which is actually my home, more like rubbers and plastics, but things that don't necessarily behave linearly. So here you've got sort of springs and large deformations, or materials that might have a nonlinear stress-strain law. After that, we'll look at dynamic analysis. So if we've got a load that varies over time, or if we've got a static load and we look at the response over time. So something where over time, either the load or the response that we're looking at changes. So as you can see, we're getting into more complex things and things that might have more real world applications. We'll end the FEA side, week 7 or so, with thermal problems. So can we actually add an analysis of temperature to this? So temperature gradients can be caused by heat flux in, they can be caused by prescribed temperature boundary conditions, and we'll look at how those things are affected by conduction, convection, and your sort of basic thermal phenomena as well. And that'll round out our approach to these particular problems, at least for the FEA side of what we'll be doing this semester. And again, all of this is geared toward giving you a practical knowledge of how to apply SolidWorks and the FEA aspect of SolidWorks into real-world analysis problems, so that you can go out there and use this stuff. Some folks might be asking, why are we basing this all in SolidWorks? Well, we're basing it in SolidWorks because SolidWorks is great for designing things. So you can take something from an idea into a solid model, but now we're doing the sort of next step of taking that solid model and actually analyzing it. Analyzing it for the environment it's going to see, what response is it going to give, and what that will allow us to do is then take that response and see, well, can we actually change the design to make it better attuned to the environment that it's going to be operating in. Maybe it's over-designed. There's too much material, it weighs too much. Can we actually remove some mass or change the design around such that we cut weight, but we don't lose performance or some such? Or maybe if it's a thermal problem, we see that there's not an even temperature distribution. We've got hot zones one place or another, or it's not dissipating enough heat. The heat fins aren't designed correctly. So can we modify those things within the software such that we get our design iteration, our first pass going through the software without having to do it in prototyping. Okay, basic syllabus review. You can look this stuff up in the syllabus, but we'll go over it really quickly here. Homeworks are going to be worth 75% of the total grade. There'll be 15 total, 5% each. For attendance and participation, really we're not going to be taking attendance because of the structure of the class, but we'll have participation based on assignments that'll be collected each week, small assignments worth about 1 percentage point each, so just be on the lookout for those. They'll be clearly announced. Quizzes, we'll have 4 quizzes, 2 in the front half of the class for FEA, 2 in the back half of the class for the CFD. Those will be worth 2.5 percentage points each, all for a total of 100%. The grading scale broken down here, A, A minus, B plus, B, you can see all the way down to F, so you can peruse that at your leisure. Most importantly, the course website, and we'll go over Canvas page a bit later. We will have our Canvas pages where we'll post the homework, we'll post these lectures and the modules, the notes that go with them, all other course announcements. You'll see that all in the main Canvas section, not a Canvas section for your specific your lab section, but for the main section for the class, so everybody all together. So be on the lookout for that page, and when those modules become active, we'll talk about that too when we talk about that page. For the homework, no late homework will be accepted. It's a bit draconian, but to give something back to you, we'll drop the lowest homework grades, one from the front half, the FEA section, and one from the CFD section, automatically, without need for any explanation or notice. You don't even have to tell us. We will average out the lowest homework grade, one from the front half, one from the back half, so 2 grades total. And so that's what we'll do there. Instead of entertaining people's sort of questions and rationales and their request for late homework or dropping grades. We're not going to accept anything late, but we will allow you 2 things to write off the books without question. Attendance. Since this class is being delivered completely online, all these lectures, and it'll be asynchronous, you'll be taking it at your own pace. These modules will be released weekly for the first Monday lecture, and then Wednesday and Friday lectures will come up later in the week. So you're going to be taking this at your own pace. Because of that, there's no real attendance to be taken. There's nothing to be late to. You don't want to be late for the office hours or these sort of recitation sections, and I'll give you the schedules for those in a bit because they're only an hour long, and if you miss it, then you'll actually miss your chance to chat with the TA. Now, in some instances, there are prerequisites for the lab sections, the modules that will come out. So what you have to be sure of is that you're keeping up with the modules, you complete them in a timely fashion such that you don't fall too far behind, because in some instances it's actually impossible to skip ahead. So make sure you're keeping up with those, and make sure you are keeping up with the assignments as well, and those due dates. All right, you've probably seen this on lots of other syllabi. We have your standard statements on academic integrity. You can check the link here to view the academic integrity policy for the College of Engineering. Basically, just don't cheat, right? The goal here is to do your work on your own such that you learn, such that you grow, such that you gain this knowledge. Yes, there'll be some things that you struggle with, but the struggle is life, right? The struggle is actually how you learn and how you grow and how you engage new things. If you aren't struggling, then you're likely not doing anything new. All right, challenge yourself. And if you do have questions, you can reach out to us. You can reach out to other students you know that are taking the class. But the point is, make sure you do and turn in your own work. We've got a statement on disability as well. If you need assistance in that regard, please do not hesitate to reach out to me. Don't hesitate to reach out to one of the TAs or Dr. Brower. We will accommodate you. We'll work with you to sort of help you get the most out of this class and to make it as seamless for you as we can. Okay, well, that's all I have for you now. Thank you for getting this far and watching this video. Hopefully you've got an overview of everything that we're trying to get across, where this fits in a whole sequence of things that we want you to learn, why we're going about it this way, and most importantly, the idea that, look, we're trying to give you some tools that you can use to get out there and analyze things on your own, apply these methods to problems that may be similar to what we're doing, or maybe not similar to what we're doing, but you'll have the tools to dive in, tackle those problems as they come up. So next lecture, we'll be talking about Canvas and what's going on with the Canvas site, and how to sort of keep up with the modules, where the homeworks are, how to turn things in and whatnot. So looking forward to interacting with you over this semester, and I think you're going to get a whole lot out of this course if you just dive in and try and make something happen. Okay, take care.